Okay, were there any questions? No. What I decided to do with the quiz, nomenclature quiz, is just move it to tomorrow. Because tomorrow's going to be a longer day. A little more time to fit it in. But no other questions?
I have one from homework.
Okay. Well, Appendix D is a pretty useful data table. If you look at table D5, D5 is a table of isotope masses and their abundances. And so we have the isotope masses. How do they get the isotope masses? Because we know the composition of the atoms. So, for example, hydrogen, how many protons, neutrons, and electrons in hydrogen? One. One proton, zero neutrons, one electron. Good. How about in hydrogen 2? Hydrogen 2, they don't call hydrogen 2. They give a fancy name for hydrogen 2. It's called deuterium. Hydrogen 2, what's the composition?
One proton, one neutron, one electron.
Yeah, one proton, one neutron, one electron. And then hydrogen 3, if you look at the natural abundance of hydrogen 3, which is tritium, do you see that? It's really negligible. Hydrogen 3 is a radioactive isotope of hydrogen, so it's not stable. And so when we're looking at it, we'll just consider hydrogen and deuterium. So we know what the atoms are composed of just based on these symbols. We call the nuclear symbols. Nuclear symbols have this number. This number on top is called the mass number. And there's a Z, an A and a Z. The Z is often not written, but that would be the atomic number. And that tells us the number of protons. But each element is defined by the number of protons it has. So based on the nuclear symbol, we can figure out the composition. If we know the composition, how many protons, how many electrons, how many neutrons, then can't we just sum up the individual masses of the protons, neutrons, and electrons to get the mass of the isotope? The answer is no. This number here, the mass of the atom, does not equal the sum of the masses of the protons, neutrons, and electrons that make up that atom. And why is that?
Mass defect.
The mass defect. And so, did I talk about the mass defect? Yeah, okay. Basically, some of the mass is converted into what we call the nuclear binding energy. And so the mass defect is just to hold all the protons together. What holds the electrons to the atom is the nucleus. The nucleus, tiny nucleus, and all the positive charge is concentrated in the nucleus, and the electrons are in mostly free space. We call this the nuclear atom model. And so the electron is held to the nucleus by what type of force? And so let's take a look at the forces in nature. What are the forces? Gravity. Are the electrons held to the nucleus by gravitational forces?
No.
Are there gravitational forces between the electron and the nucleus? Yes. Anything that has mass will be a gravitational pull. But in this case, it's so weak, we say it's negligible. So we don't really worry about gravitational forces. In fact, in chemistry, we don't really worry about gravity at all. Sometimes this can lead to trouble. For example, chemists don't really differentiate between mass and weight. But physicists for sure are going to differentiate between mass and weight because they're different. But, you know, the force of gravity is not really changing in the laboratory. It's not to say that chemists aren't interested in gravity. You know, on the space shuttle, they're looking at growing crystals. You know, do crystals grow differently in a weightless environment versus on Earth? You know, does gravity have some impact on how crystals nucleate and grow?
And doesn't it have to do with pressure? So could gravity definitely be a factor?
Could be. You know, these are all questions, but usually pressure impacts all sides. And so it impacts all sides. We call it, yeah, rather than, you know, just straight down. So different.
Are chemists concerned with kinetic or potential energy?
And gravity?
And just so we're talking about, you know, like the nucleus, how it's being held.
Yeah, there are certain things where gravity plays a role, like gravitational filtration. We do that kind of stuff. And then it could, you know, like if the atom is going down towards the center of the Earth, or if the atom or molecule is going up, you know, that could impact things like velocity and that type of stuff. But for the most part, do chemists worry about gravity at all?
No.
Not at all. Not at all, unless they're doing some obscure. What chemists are most interested in are what forces? Electrical. Pretty much electric. Magnetic somewhat, but we call it electromagnetic since they're related. But primarily electrical forces.
Are we recording this?
Yeah, good question. This morning I attempted to record and it failed, so I didn't capture. I only got 3 minutes of it this morning. Electromagnetic forces. And so what holds the electron to the nucleus is the negative charge in the electron is attracted to the positive charge of the nucleus, or more specifically, the positive charge on the protons, because the neutrons, do they have any charge? No, they don't have any charge. Those are the electrical forces that hold that. But in the nucleus, there could be one or more protons. If there's more than one proton, what's holding the protons together? Is it electrical forces that hold the protons together in the nucleus?
No.
No. And so there must be a force that's stronger, more powerful than electrical forces, because it has to overcome the electrical repulsions that the protons would experience. The nucleus would want to break apart. And so electromagnetic forces, this is around chemistry, or electrical forces. You know, chemists are somewhat interested in magnetic forces as well. Sometimes the nuclei, even the electrons, can act like little magnets, and they can interact with other magnets, like the Earth's magnetic field or external magnets. But primarily electrical. And so what holds the protons together?
Weak nuclear.
Yeah. The nuclear forces. Well, nuclear forces, when we look at those, there's the weak and the strong. And it's the weak nuclear forces that hold the nucleus together. But weak is relative to what? Is it weak relative to electromagnetic? No, electromagnetic forces are much weaker than the nuclear forces. They have to be. Otherwise, the nucleus would fall apart. And so the weak are, I guess, weak relative to the strong nuclear force. The strong nuclear force, you know, when we dig deeper into it, protons, do you know what protons are made up of and neutrons are made up of? Quarks. And so, you know, the things that hold the quarks together are the strong nuclear force that makes up the proton. But we don't have to go that deep. You know, for us, there are three subatomic particles: the protons, the neutrons, and electrons. And this is our way of understanding the properties of atoms. And so these weak nuclear forces hold the nucleus together, and we call that the nuclear binding energy. And nuclear binding energy is given by delta E is equal to delta mc squared. I talked about this equation already? Mm-hmm. So that's it. This is the realm of nuclear physicists and nuclear chemists. And so it's a different set of rules, a different set of forces. And so for us, we're just primarily interested in electrical forces. If we're interested in nuclear physics, then we'd be looking at the weak nuclear force. Okay. And so what we're going to do is we're going to look at our three subatomic particles here: the electron, the proton, and the neutron. And there are some things that you should know about the electron. One is how much it weighs. How big is it? Well, how big is it is how big is an electron? Do you know how big an electron is? It's got to be small, right? I mean, if the nucleus, like for example, how big is the nucleus? Did I talk about this already? I think I might have forgotten to talk about it in the morning class. But if an atom is 1 to 6 angstroms, or 100 to 600 picometers, right? We talked about that? Yeah. Then the nucleus is about 10,000 times smaller. But how big is an electron? An electron's got to be smaller than that still, right? And so do you know what the answer is? How big an electron is? Well, if somebody asks you, what's the size of an electron? The size of an electron is 0. How could the size of an electron be 0? How the size of an electron can be 0 is because of, and electrons are very difficult to describe. Because electrons aren't like anything that, that we can relate to in our physical world. And so what people say of an electron is like this point in a field. And it's a point in this, have you heard of this Higgs field thing? And so it'd be that, but we'll talk more about the electron later. And so the size is really weird for an electron, whereas the proton does have a finite size and the neutron does have a finite size to it. So that can be measured. The mass of an electron can be determined. Do you know how the mass of an electron was determined? Or actually, let's take another step back. Do you know a couple of things? One, this nuclear atom model came from who or what experiment? Rutherford. And it was the Rutherford, and it's a famous experiment. It's called the Rutherford blank experiment. Yeah, Rutherford gold foil experiment. And what did Rutherford do?
That's what I'm looking for. They basically foiled the plum pudding model.
Yes. There's another model. The nuclear atom model is the one that fits the observations from the Rutherford experiment. The Rutherford experiment did what? And I did talk about the size. Is there a hard shell around this atom? No. Normally when we think of atoms, we think of these spherical objects. But how big is an atom? Well, it depends on where you put the probe. If the probe's here and the electron's over there, maybe it's a little smaller than if you put the probe here, right? But really, this electron's all over. We have a little probability cloud. But the probe, it depends on what you probe this with. And that's going to dictate how big this is. And so there are different ways you can probe this. One is you can bond this atom to other atoms. But when you bond, like, say, carbon, you form a carbon-carbon single bond. Carbon-carbon single bonds are kind of long. And then you have a carbon double bond, carbon-carbon double bond, carbon-carbon triple bond. Carbon-carbon triple bond is the strongest and the shortest bond. And so if you're looking at a carbon atom in a carbon-carbon triple bond versus a carbon atom in a carbon-carbon single bond, the carbon atom seems smaller in the triple bond and bigger in the single bond because of the distance. And so normally when we think about atomic radii, it's kind of just this average. You know, depends on what it's bonded to. It depends on what you probe it with. If we probe it with the same thing and come up with the same electrical potential, you know, we probe it, eventually it's going to meet some resistance depending on the charge on the probe. And if we come up with a consistent distance, then that's what we'll call the radius. We know orbitals. You know, orbitals have this boundary. What do we call that boundary? The orbitals. You know, the orbitals have a shape, like an s orbital has a shape, it's spherical shape, and it's kind of got the shell around it. And what does that shell represent? That shell represents
Orbital clouds.
Yeah, the orbital cloud. It represents a probability. So, for example, if I have a 1s orbital like this, inside this boundary, there is a what percent chance of finding an electron? 95% chance of finding an electron inside this boundary. And outside the boundary, there's a 5% chance of finding an electron. And so that's another way we can kind of get a gauge of the size of things. But the size of an atom isn't so precisely defined. You know, we look at the tables, but those tables consist of average radii. But anyway, we have an atom like this. Let's say this is our atom. Gold will have lots of protons in the nucleus and lots of electrons. And the electrons pretty much occupy empty space. And how did Rutherford conclude that? How did Rutherford conclude that the electrons occupy mostly empty space?
By shooting particles out.
By shooting particles. And what were the particles?
Alpha particles.
Alpha particles. Alpha particles are helium nuclei. The electrons have been stripped off. So it's an He2 plus, no electrons. And it's this helium-4 isotope here. Although there's one other isotope of helium. Do you see it? The other isotope is helium-3, but look at the abundances here. But, you know, this particular particle here, this is the alpha particle. It's shot, most of the alpha particles go straight through and hit the detector. And that's what led to the observation that the atom consists mostly of empty space. Some of the particles are going to bounce back, and so they hit the atom and bounce back. But what did they hit?
The nucleus.
Yeah, they hit the nucleus and bounce back. And the nucleus is positive, the alpha particle is positive, and so it's going to be the electrical repulsions. You know, you're trying to force two positive particles together, they're going to repel each other. And so this is what caused it to bounce back. And so that's what led to the idea that all the positive charge is concentrated into the nucleus. And so we have that. And so you should know some key experiments, historical experiments. One is the Rutherford gold foil experiment. The other is regarding the electron. Do you know who's credited with discovering the electron? And so for the electron, we look at J.J. Thomson. J.J. Thomson, and the experiment that he did was the CRT. CRT, do you know what CRT stands for? No. CRT stands for cathode ray tube. Oh, I can make you watch that out again. Mm-hmm.
There's a quote from Rutherford about atom.
Okay.
It's the splitting the atom is like trying to shoot a gnat in the Albert Hall at night and using 10 million rounds of ammunition on the off chance of getting it. That should convince you that the atom will always be a sink of energy and never a reservoir of energy. That was his quote.
Oh, wow. That was in reference to what?
So like the Royal Albert Hall is the big concert venue or like a show venue.
I mean, he was trying to talk about energy, sink of energy versus reservoir energy.
Yeah.
Interesting. Yeah, actually, Rutherford had another major discovery. Do you know what the other major discovery Rutherford did? Rutherford did the nuclear atom model. J.G. Thomson did the electron, but do you know who did the proton and the neutron? Actually, Rutherford did the proton. And then another person, Chadwick, did the neutron. So those are the key subatomic physics discoveries. But we'll talk a little bit more about that. But Rutherford hypothesized the existence of the neutron. Rutherford hypothesized the existence of the neutron, but he didn't discover the neutron. The person who was credited with discovering the neutron is Chadwick.
So I think the point of going back to Rutherford is, think of it as the nucleus as being as small as a gnat, and you're sitting there trying to
hit the gnat
in complete darkness.
In complete darkness with huge amounts of ammunition, huge amounts of alpha particles. Oh, that makes sense.
Yeah.
Now I get that. A little gnat in a gigantic hull that's as big as a nucleus in an atom. Then, that puts it quite well visually. And then you're hitting it, so most of the particles will just go straight through.
Yeah.
And then once in a while, you get lucky and hit it. Oh, that's cool. All right, so let's take a look at this here. All right, what you're seeing here is a cathode ray tube. The cathode ray tube is just a tube, and what they do is they try to run a lightning bolt through the tube. But in a normal lightning bolt, a lightning bolt goes all kinds of random directions because it strikes molecules bare. But in this lightning bolt, it just goes straight across the tube. The reason it goes straight across the tube is because they put a low pressure gas in there. In other words, they put a vacuum pump and suck out most of the gas. And then they usually fill it with just a pure gas, argon or something else, neon, whatever. Okay, and then how do you generate a lightning bolt? How you generate a lightning bolt is you have some high potential, high voltage. And so let's say up in the sky, there's some negative or positive buildup, charge buildup, and down on the ground, there's some other charge buildup. What is it? Positive charge buildup, let's say. And so we do the same thing here in a cathode ray tube. This cathode ray tube is not very visible, but there's a tube here that's most of the gas has been sucked out of the tube. And so it's very low pressure gas in here. And then they put a piece of metal over here and a piece of metal over here. And then they'll attach this to a powerful battery or power supply. And what they'll do is they'll put a charge on one of these, a negative charge over here. and a positive charge over here. And they'll crank up the voltage, and eventually what you're going to have is a little lightning bolt that occurs. It's a little bit more complicated than that. Now, you can't see it, and so it's invisible, these rays. These are called cathode rays, and the cathode rays are just beams of electrons. And so what they do is they put a plate, a phosphorescent plate, so when the electrons strike the plate, the phosphorescent material on the surface of it starts to glow. And so this is why you see the glowing here. It's because the electrons are striking the plate here. And so the electrons are being generated here and then traveling over to this. In other words, electrons are being generated at this electrode, the negative one, and being pulled towards the positive electrode over here. All right, so the cathode rays were mysterious, and it wasn't until later that it was discovered that these consist of fundamental pieces of atoms. In other words, it didn't matter what they changed the metal to. So if they use copper here, they got cathode rays. If they change it to gold, they get cathode rays. If they change it to platinum, and so regardless of the metal, aluminum, they always got the same cathode ray. And so the conclusion for that is that cathode rays for this beam of electrons are a fundamental part of all matter. And so they're found in all atoms. But you need a conductor, you can't have an insulator work as electrode. So they didn't test every single material, but that was what they learned from those observations. Okay, these cathode rays must be negatively charged because they're being attracted to the positive plate. Not only that, if they put a metal plate here to block the beam, the metal plate acquired a negative charge. And so from this experiment, they got that the electrons are a fundamental part of matter and that they have a negative charge. But what is the charge? Well, they know it's negative. Okay, the next thing is these beam of electrons, this electric current interacts with magnetic fields. So if you bring a magnet, let's say north pole of the magnet will deflect it one way, the south pole of the magnet will deflect it the opposite way. And so here we have the cathode ray. We used to have a CRT too. And they're going to bring a magnet. There's a left hand and right hand rule to show which way it's deflected, depending on the charge. It's positive or negatively charged. So here they bring in a magnet, and do you see it's deflected by the magnetic field? Okay, that also tells us, and the direction of deflection tells us the charge. So this also verifies that these are negatively charged. And go back here. And if I flip the magnet over, it'll flip the cathode ray deflection downward. In some ways, actually, in a lot of ways, this is similar to the mass spectrometer. Do you remember how the mass spectrometer weighed particles? It took charged particles and deflected them using a magnet. And so, if there were heavy particles, were they highly deflected? No. If there were heavy particles, they weren't deflected much because of their inertia. However, if there are light particles, then they're highly deflected. So light particles are highly deflected, heavy particles aren't. And so the angle of deflection here depends on how heavy the particle is. The heavier the particle, the smaller. The lighter the particle, the larger the angle of deflection. And so this is just typically a quartz glass tube. Oops, is that mine? Typically, this is a quartz glass tube, like this. And so you have it striking here, let's say. And so what we need to do is we need to calibrate this. Do you know what we use to calibrate the mass spectrometer? Carbon 12, because we know that carbon 12 weighs exactly how much? So all we have to do is feed in carbon 12 here and see where it lands. And then we know that that point is exactly 12U, and then figure out, based on where these land, how much it weighs. I'm just using some physics. However, back in J.J. Thomson, this is back in the 1800s, getting close to the 1900s. Do you think he had some graphite and a laser to vaporize some graphite and then introduce some carbon-12 atoms in here? Do you think? No, he didn't have that. And so how did he calibrate this to figure out the mass of the electron? He didn't. And so what he got was the mass to charge ratio. He couldn't get the mass, and he couldn't get the charge. You know, all he knew is this is a negative particle, but what is the charge, the magnitude of the charge? You know, just the mass to charge ratio, because, you know, the higher the angle, the lighter, the lower the angle, the heavier. And so using a little bit of physics, you get the mass to charge ratio. And so there are two unknowns here. The mass of the electron is an unknown, and the charge on the electron is an unknown. So that's two unknowns in one equation, the mass to charge ratio. So if we have two unknowns in one equation, what do we need to solve this? We need two equations. And so what was the second equation? Where did the second equation come to figure out what those were? And so the second equation came from Millikan, R.J. Millikan. And do you know what Millikan's famous for? J.J. Thomson's famous for the CRT and the electron. Millikan's famous for, and they have one of these set up at Griffith Observatory. That's the first one I saw. You look through a little telescope and you watch these little things fall. Have you seen it? The little things that fall are little tiny oil droplets. And so Millikan's famous for the oil drop experiment. I think in physics they just got one of these, Millikan oil drop apparatus. And in the Millikan oil drop experiment, they have a little sprayer that sprays a fine mist of oil. And this fine mist of oil will populate this chamber here. Do you think when he sprayed that fine mist of oil, all the oil drops were exactly the same size? No. You know, some of the oil drops were big, some were small. And there were a bunch of them. And so when you have a range of oil drop sizes and a population, do you know what we call that? It's diversity for sure. But sometimes we can map it out. What do we call it? We don't use the term diversity. We use another one that starts with a D, I. Starts with a D, I, D, I, S. Distribution, right? We call it distribution. And so something like this, we probably expect, you know what normal distribution is, or bell-shaped distribution? A bell-shaped distribution is most of them are going to be kind of in the middle here, but on the extreme ends, you'll have extremely tiny oil drops, and on the other end, you'll have extremely large oil drops. And so we'll have a distribution of oil drops in here. But whatever, the oil drops are going to just float down to the bottom of the container and collect down here, right? And that's due to what force? Oil drops falling down to the bottom of the container is due to gravity. And so gravity is here, and those are going to fall. And so he had a little telescope that he was watching these oil droplets fall. And you could do the same thing. You go to Griffith and look through the telescope and watch the oil drops fall due to gravity. Some of the oil drops are going to be small, some big. There's going to be a range of those. And so we expect a distribution of oil droplets. But what Millikan did was he did this. He gave the oil droplets a charge. Normally the oil droplets don't have any electrical charge, they're neutral. But what you can do is you can introduce a source of ionizing radiation. What does ionizing radiation do? Yeah, it knocks electrons off matter. And so if you knock electrons off air, those electrons go somewhere. Those electrons can collect on the oil drops, or you can knock electrons off oil drops, or whatever. And so we have some ionizing radiation in here. And what that's going to do is it's going to create charged oil droplets. And let's say we ionize the air. We knock electrons off air, those electrons collect on the oil droplets, and we get charged oil droplets. And then what we do is we put an electric field in here. Electric field just be like a voltage we saw earlier. So for example, here, what we could do is we could put a piece of metal in here on the bottom. And this piece of metal will be negatively charged here, by putting a battery or power supply here. And then this piece of metal at the top will be positively charged. And so these negatively charged oil drops will be attracted to the positive. So what we're going to have is we're going to have a fight between the force of gravity and the electrical forces. Sometimes gravity wins out. Let's say there's only one electron on the gigantic drop, it's going to fall down because there's not enough electrical force to pull it up. But eventually we'll hit some droplets that, don't fall. And so this drop might fall down here. This drop might just stay static. And this tiny drop might actually be pulled up. And so you'll see these tiny drops maybe going up or highly charged drops going up. And so he knew he had this population, and then what he did was he figured out, what the smallest amount of charge could be. And then he figured out, well, the smallest amount of charge will be the charge on a single electron. And so from the Millikan oil droplet experiment, he got the charge of an electron. And the charge of an electron in coulombs, which is the usual unit, is 1.6. What is the charge? 1.6. A more precise and accurate charge has been determined with better data here. But let's see, the charge. I think it was 1.6022. Verified times 10 to the minus 19 coulombs. Let me put a little question mark. I'll look it up. I don't have it memorized. I don't have it memorized because we usually don't, unless you're doing a physics problem, we usually don't represent the charge of an electron here. And so this is the smallest fundamental unit of charge, which means that, for example, can we have 1.5 times 10 to the minus 19 coulombs? Is that possible? No. Or half of this. Can we have half an electron? Is that possible? No. And so this is the smallest fundamental unit of charge. Therefore, we define this as minus 1 unit of charge. And so this would be minus 1.60 times 10 to the minus 19 coulombs. C stands for coulombs here. And we can have 2 electrons. That would be double. 3 electrons would be triple. When we have this is varying by integers. We could have 1 fundamental, 2 fundamental, 3 fundamental, but we can't have 1/2. We can't have 1.5. We can't have 1.1 or any other. It has to be an integer number. You've seen that before. What did we call that? Rather than continuous, we called it It's not continuous. It's starts with a Q.
Quantized.
Quantized, right. Quantized. And so, based on the behavior of oil drops, he could figure out that all the charges had to be multiples of this charge. And since all charges have to be multiple, we just talk in terms of the multiple of charges. -1 means one of these. -2 means two of these, etc. Right. So if we have the mass to charge ratio and we know the charge, what can we calculate? The mass. And so, based on these two experiments, combined, we use dimensional analysis. The mass to charge ratio is our conversion factor. And so we start off with a given, the charge, cancel out the charge, get the mass. And so using dimensional analysis, the mass of the electron was determined. And the mass of the electron was what? 9. Yeah, I don't have it memorized. 0.05 U, I do have memorized. But, okay, now the size of the electron's tricky. That's because it's just some point in some field. Okay, what were some of the other key experiments? So we talked about J.J. Thomson, talked about Millikan. The proton was discovered by Rutherford. You don't need to know that. And the mass of the proton was determined using CRT. The size of the proton was not discovered by Rutherford. The neutron, though, is a bit more tricky because the neutron, is it going to be deflected by magnetic fields? If you have a beam of neutrons, will a beam of neutrons be deflected by a magnet? No. It has to be a charged particle in order to be deflected by a magnet. And so, how are neutrons discovered?
You can do size.
Yeah, you could do the size, but they didn't know the size. Yeah,
I think what remains after you separate positive and negative charges, possibly.
Sort of like that.
The protons and neutrons, and the electrons, what's left.
Well, it was hypothesized and then finally discovered by Chadwick by looking at deuterium. What does the nucleus of deuterium have?
One proton, one neutron.
One proton and one neutron. And then Rutherford determined the mass of the proton. And if we know that the deuterium has one proton plus other stuff, the other stuff we could figure out the mass of that, and by subtraction. And so you could just take the mass of the nucleus minus the mass of the proton. That gives you the mass of the neutron. But there's one thing that could complicate that, and what is that?
You don't know the mass of the electron.
Well, we do know the mass of the electron at this point because these discoveries happened afterwards. The mass defect.
Oh,
Yeah. And so, is the mass defect significant? Maybe it's not significant. And that's how they got the mass of the neutron, by doing that subtraction. But normally these particles aren't additive. But anyway, the proton and the neutron you don't have to worry about. It's just for general interest here. So these are the experiments that you should worry about. And these are the ones that show up on tests, on standardized tests. I don't really do too much with these. All right. Well, if you're if you're into atoms, atomic structure, one of the things you'd like to know is how many isotopes they're going to be. And so if I have element number 10, how many isotopes are there? 3. But what we want is a theory should be able to predict that. And so if we understood the theory, then we should be able to predict how many isotopes there are. Not only that, we should be able to predict how much mass defect each isotope will have. And then, therefore, we should be able to determine the mass or predict the mass. And not only that, we should be able to predict these. These are the percent abundances. So good theory, we should be able to predict this. Now, what was the theory that underlies chemistry? The theory underlying chemistry was the quantum mechanics. But the theory that underlies this, this is different because this is, when we talk about the nucleus, this isn't really the realm of chemistry. It's the realm of what? Physics and nuclear chemists. Physics and nuclear chemists are into this. And so you should ask a physicist or a nuclear chemist, if I have an atom atomic number 10, how many isotopes? How much do each of those isotopes weigh? What is the percent natural abundance of each of those isotopes? And if they can tell you, they can predict this, rather than, how are these numbers determined? These numbers are determined by experiment. This is our two-pronged approach in science. Our two-pronged approach in science is we do both things, theoretical and experimental. This is purely experimental here. We'd like to be able to derive this theoretically. That way you don't have to feed these things into a mass spectrometer. Save yourself a lot of time and work. And so if we could do this theoretically, then those are the types of things. And so do you know what the theory underlying this type of stuff is for nuclear chemists, particle physicists? You know what they call it?
Just a second. It's theoretical and experimental. One is qualitative, the other is quantitative.
Theoretical and experimental, both can be qualitative or quantitative. It just depends. Experimentalists will take measurements. We'll measure all these things using mass spectrometer. A theoretician will do calculations using the theory. But the calculations can be qualitative. That is, okay, just do a crude, back of the paper napkin calculation versus a thorough, what they call, they have different words for this. Have you heard these words? Like for different levels of calculation. Have you heard of things like ab initio or empirical? Empirical is just from observations, it's a simple equation. But then, you go to different levels of calculation. And so you have 100% theoretical calculations, they give a name for that. And then you have calculations based on experimental data. They have a name for that, empirical versus ab initio. And then they have these semi-quantitative, semi-qualitative, whatever. And it depends on how much computational power you have. But anyway, we'll get back to this. So the theory that underlies the atom here, we aren't going to look at. And so if you wanted to know how many isotopes there are, you'd look it up in a table. This is purely experimental observational data. Or what their percent natural abundances are, you'd look it up in the table. But it would be great if we could do this theoretically, and the theory actually is pretty well developed. The theory is called the Standard Model. Have you heard of that? The Standard Model? There are lots of videos on that, so if you're interested. And this is the type of stuff they're into, the quarks and whatnot. Although we're not going to get into it. However, we'd like to get into it a bit more than this. Because when you look at this, what do? We have a bunch of observations. What's the scientific method do next? We look for patterns and trends. So do you see any patterns here? And so the next thing is we look for patterns. Well, hydrogen is 2 isotopes. one radioactive. Helium has 2 isotopes. Lithium has 2 isotopes. So the pattern's 2 isotopes. Does everything have 2 isotopes? No, because when we get to boron, or beryllium, actually boron has 2 isotopes. When we get to beryllium, there's just 1. When we get to oxygen, there's 3. And fluorine's back to 1. So is there a number pattern there? 2, 2, 2, 1, 2, 2, 2, 3. Do you see a number pattern there? No, there actually isn't a number pattern there. Do you see any other patterns there? So we'd look through all the data. Calcium has 6. We'd look through all the data and see if we could find a pattern. Sometimes the patterns are very difficult to see. Sometimes they depend on a number of factors. But there's no simple pattern here. And so it makes it hard to predict. There are some patterns here in terms of the natural abundances. When you look at the natural abundances, it appears that the even numbered ones are better than the odd numbered ones. But it's not a consistent, it's not as consistent as you'd like. And so therefore they call it a rule. It's called the even odd rule. The even odd rule is that even numbers are better than odd numbers. That's the even odd rule. So it seems to hold here, with maybe some exceptions. Look at nitrogen 14 versus nitrogen 15. You see that? Even way higher abundance. Way higher abundance implied more stability. Look at oxygen. Oxygen 16 and 18 are greater than 17. It's even odd.
It doesn't work with boron.
Yeah, it doesn't work there. We have to look a little bit deeper. It doesn't seem to work because lithium has 3 protons. And if you have 3 protons, lithium-6 would have how many neutrons? 3 neutrons. And it's 7.59. But lithium-7 would have how many neutrons? 4, so that's even, so that makes it better. So this is odd-odd, this is odd-even. And so odd-even is better than odd-odd. And so we just look at it a bit deeper, and then it kind of works. But it doesn't really work for this. But it's a rule. And then there are other rules that we can get from this. But all those rules should be, should match whatever theory there is. And apparently, the standard model does a pretty decent job of predicting a lot of things. So it's what we use. But we're not going to be looking at that. We're just going to be looking at the electrical interactions and what dictates the chemical interactions between these. All right, so let's do some more with isotopes. Here. So if you have a cup of water, are all the water molecules exactly the same? No, they aren't. What's different about the water molecules in a glass of water? Yeah, the mass. One of the big things is the mass. Water consists of a hydrogen, an oxygen, and a hydrogen. And looking at the hydrogen, we have 2 choices of hydrogen atom. The hydrogen might be an hydrogen 1 or a hydrogen 2. So we have an H1 or an H2. For the oxygen, what do we have? When we look at oxygen in nature, there are 3 different oxygen atoms, isotopes of oxygen. We have O16, O17, and O18. O16, O17, and O18. And this hydrogen can either be a hydrogen 1 or hydrogen 2. And so these are the pieces that make up water, all of the pieces. Because, based on experiment, these are the isotopes that are found for these particular elements. And so that means if we take all these isotopes, how many different water molecules could we build? 9? 9's correct. What are they? Well, if you don't see that they're 9, we could just build them. And so let's just build them one by one. And so the first one is we can use a hydrogen 1 bonded to an oxygen 16 bonded to a hydrogen 1. And so that's one molecule. What's the next molecule that we can come up with? Yeah, hydrogen 1, oxygen 16, hydrogen 2. But this one is a bit tricky because of this. When we're building these, we put the hydrogen 2 on the right hand position and not the left hand. What we could have done is this. We could have put the hydrogen 2 in the left hand position and the hydrogen 1 in the right hand position, and then we generate the same molecule. And so you look at these and you go, these are the same thing. I just got to flip this 180 and I'll have exactly this, correct? It is exactly the same molecule, except there are two ways of building it. When we have two ways of building it, that changes the probability of building this molecule. If there are two ways to build it, it actually doubles the probability of building this one. Okay, what else do we have? We could have a hydrogen 2, oxygen 16, and a hydrogen 2. And so that's 1, 2, 3. This is 3 molecules. 1, 2, 3. Okay, then what? And then what we do is we just repeat it. Number 4, we'd go hydrogen 1, oxygen 17, hydrogen 1. 5 would be hydrogen 1, oxygen 17, hydrogen 2. Or there are two ways of building this one, right? We could have the hydrogen 1 first, or we could have the hydrogen 2 first. So that would be hydrogen 2, oxygen 16, hydrogen 1. Hydrogen 2 is also called deuterium. People don't usually call it hydrogen 2. Oops, oxygen 17. You're right, because this is the same as 2B. So that would be 5. What would number 6 be? Yeah. Three more. Can you guess what they are? Three more would be hydrogen 1, oxygen what?
18.
And so that would be 7. 8 would be oxygen 18, hydrogen 2, or hydrogen 2, oxygen 18, hydrogen 1. 9 would be hydrogen 2, oxygen 18, hydrogen 2. Then we ask ourselves, did we do all possible combinations? Is this all of them? Can you think of any others? No, this is it. And so when you have a glass of water, you actually drank 9 different water molecules. What's the difference? The difference is in their mass. For molecules, we can represent them like this, or we can represent them like this. We can represent them like this, or like this. When I write H2O, this is the combined mass number. The combined mass number would be 1 plus 16 plus 1. And so this gives the total number of protons and the total number of neutrons in the entire molecule. And so this is H2O with a mass number of 18. Is that the actual mass? No. And then what's the heaviest? This is actually going to be the lightest water molecule. The heaviest water molecule will be
H2O.
Yeah, H2O with a combined mass number of 22. And it's a bit heavier than that. And so these are called heavy water molecules here, and then we have the lighter water molecules over there. Now, what's the actual mass? The actual mass is, we would have to go to our table here and then look up the masses. So for example, hydrogen's mass is 1.007825. But when we look at the periodic table, I look at the periodic table and it tells me that the hydrogen mass, the black number here, is 1.00794. Why the difference in the masses here? On the periodic table, I get 1.00794 for the atomic mass. And over in this table, I get a 1.007825. Not the mass defect, but something else.
You said those were light water molecules?
Yeah, these are the lighter water molecules, and these are the heavier water molecules.
Isn't that one the average of all?
Yeah. The mass in the periodic table is not the mass of the individual isotopes, it's the weighted average mass of all the isotopes, all the naturally occurring isotopes. And so if I were to average hydrogen and deuterium, then it comes out to 1.00798. But it's a weighted average, and since hydrogen 1 is much more abundant, the mass, the average mass would be 2. If this were a 50-50 split, then it'd be 1.5, the average mass. If this were, 1 and 99, then the mass would be much closer to 2 than 1. But the average is going to be, in this case, much closer to 1. Here, if we look at helium, which one's more abundant? Helium-4. Helium-4 weighs 4.002603. It's 99.999863% abundant. When we look at the average mass of helium, the average mass of helium is 4.02602, which tells me that it's much more heavily weighted in helium-4 than in helium-3, etc. You can do the same thing for lithium and others. All right, so what we'll do is, if we want to figure out how much this water molecule weighs, then we need to know the mass of H1. The mass of H1 is 1.007825 U. Then we need to know the mass of O16, not the average mass, but the actual mass of O16. The mass of O16 we get from the table. It's 15.994915 plus 15.994915 plus the mass of H1, 1007825 E. Are we going to have to worry about mass defect? And the answer is no. Why don't we have to worry about mass defect here? I'm just adding up the weights of the individual atoms. And the reason I don't have to worry about mass defect is because what holds the atoms together? What holds the atoms together is a chemical bond, not a nuclear force. It's just a chemical bond. And chemical bonds are electrical in nature. And so it's just electrical forces. We don't have to worry about mass defect. And so how much does this water molecule weigh? Well, let's go ahead and calculate that. I'm just going to do 1.007825 times 2 plus 15.994915. 18.01. How many sig figs am I allowed? Well, when you're doing addition, do you worry about sig figs? No. What do you worry about?
Decimal places.
Decimal. So how many decimal places am I allowed? 1, 2, 3, 4, 5, 6. 2, 4, 6. Yeah, 6 decimal places. So it's going to come out to 18.01. So this thing weighs 18.010565 U. So much. So it's very close to the mass number. The mass number and the mass are close, but they aren't the same. The mass number is 18. The actual mass is 18.01. Do you know what the average mass of a water molecule is? The average mass of a water molecule is this. You take the average mass of hydrogen off the periodic table, 1.00794, and then you take the average mass of oxygen, which is 15.9994, and then you get 18.02. So the average mass is slightly heavier than this. Why? Because we have heavier water molecules that are contributing to the average. In fact, the heaviest is going to be closer to 22U. It's going to be close to 22U, but not exactly 22U. And that's because I'm going to add up the deuteriums. Let's figure out how much the heaviest water molecule weighs. It's 2.014102. So 2.014102U. And then we're just going to times that by 2. We got 2 deuteriums plus an oxygen 18. Oxygen 18 weighs how much? 17.999160. So here I'm going to be allowed, this 2 is exact. So I'm going to be allowed how many sig figs? And that's going to translate to 6 decimal places and 6 decimal places. So I expect 6 decimal places in my mass. So let's go ahead and calculate that. 2 times 2.014102 plus 17.999. 22.027. $364. So the heaviest water molecule you drank today weighed this much. The lightest weighed that much. There. How much heavy water did you drink? Is it bad to drink heavy water? Well, we drink it, but the density of heavy water is going to be a little bit more dense. You know, the density of water is about 1. That's the average density of all these combined. If I just have heavy water, it's more dense. Actually, I used to use heavy water. I used to use heavy water, well, not the heaviest water. I used to use deuterated water. Deuterated water, you can buy this stuff. It just contains H2O, H2. Now the oxygen can be either oxygen 16, 17, or 18. But the hydrogens have to be deuterium or hydrogen 2. So when you pick up a bottle of this, it feels heavier than just plain water. But not that much heavier. There's an interesting YouTube. Can you drink heavy water? I used to think, yeah, it's the same. Heavy water, light water, doesn't matter. Water's water, right? But, you know, there's some subtle interactions that depend on things that could happen in your body. One of them is like density. It's more dense. The other is the bond. You know, if you have a deuterium and oxygen bond, how does it compare to a hydrogen 1 oxygen bond? Well, it turns out it's slightly different because there's more inertia. You know, it's a heavier hydrogen. There's things called chemical exchange where the hydrogens break off water. And so you expect, you know, some hydrogens to break off more easily than others. You know. Yeah. And that can impact how things react as well. But check it out if you're interested in this heavy water. Okay, drink. But anyway, how much heavy water did you drink today? A lot? Probably a really small amount. Uh-huh.
We are talking about science in heavy water and light water and how they go together. Is a hydrogen isotope more likely to bond with a oxygen 16 isotope than it is to a oxygen 17 isotope?
Yeah.
Is there an interaction that makes them more?
Well, the reason it's more likely to bond is because when you have a sample of oxygen, it's mostly oxygen 16.
No,
So
no,
just
but
in sheer terms of population.
No, what I don't mean by amount, but rather by interaction,
Like the interaction, yeah.
Does it want to bond to 16 more than does it want to bond with 17? I don't know if I'm explaining it.
Well, okay. That's a good
It's more
question.
likely.
That's a good question, but the situation is what holds the bond together? Electrical forces. And if it has an extra neutron or two neutrons, is that going to change the electrical force? No, it doesn't change the electrical force. So if you're looking at it purely from electrical forces, you would say no, there's no difference. And there's no difference because you know, we got one proton there, and the neutron doesn't impact this. And we have 8 protons over here. 8 protons, but we have more neutrons here. 10 neutrons versus 8 neutrons here. But it turns out it could, well, according to, can you drink heavy water? This made me rethink that. Maybe there is something to the mass. Normally we don't think in terms of gravitational, but maybe there's something that's missing that helps with the chemical exchange, that is the breaking up. I would expect gravitational to be a minor factor here, but there's something with inertia. That is, in order for the hydrogen to come off, it just doesn't fall off. In order for the hydrogen to come off, there has to be a collision. And so if there's a collision, then the mass could make a difference. Because if there's a collision, you have to break it off due to some force that happens in the collision, then something that's more massive is going to have more inertia. And so if it has more inertia, it's going to be slower, to move than something that's lighter, because deuterium is twice as heavy as hydrogen. And so, in terms of thinking in terms of diffusion, effusion, those types of processes where things move, lighter moves faster. And so that could change what we call the kinetics of it. Kinetics is how fast things react. And that kinetics could be important in biological processes. So this is very important in biology. So for example, if you were to eat sugar, like table sugar, and you didn't have any enzymes to digest the sugar, then it would take hours to get a sugar rush. So if you have a tablespoon of sugar, you'd be waiting hours for the sugar to digest. But you do have enzymes in your body that make the digestion happen very fast. So if you eat a tablespoon of sugar, you feel it immediately. And so the speed of reaction can have an impact, And so I would think the primary factor would be in terms of speed of reaction rather than in some kind of fundamental, difference between the electrical attractions between those two. But that's an interesting question. So, sure. Well, did we drink much heavy water today? And the answer is no, barely any heavy water we had today. They're saying for it to impact, if you watch the video, it's a very interesting video. They're saying before they predict that you'd have to replace like 60% of your water volume in your body with heavy water before you'd feel the impact of it, which is huge. You'd be a lot heavier if you did that. But if you're thinking of losing some weight by drinking light water versus heavy water, it's not going to change things much because the next thing we want to know is, what is the percent? So out of this, what is the percent H1O16H1 that I consumed today? And what is the percent H2O18H2 I consumed today? And so what we want is, we don't want the percent abundance of the isotope, we want the percent abundance of the molecule. And not just any molecule, the H2O18 molecule. And so what is the percent abundance of the H2O18 molecule? And so here we have the percent abundances of the isotopes, but we don't have a table for the percent abundances of the molecule. And so what we're going to do is, we're going to try to use some dimensional analysis to figure out what the percent is. So for example, I know the percent abundance of H1. The percent abundance of H1 is 99.9885%. And then I know the percent abundance of O16. Scroll down here. The percent abundance of O16 is 99.757. And then I have another H1. So what should I do? Should I take the 3% abundances, 99% times 99% times 99%, and that gives me? Do you think that's going to work? No, it's not going to work, because the percent natural abundance, what we're going to do is, I don't have the formula for this, but I do know the units. The unit should be percent. And so I can't take a percent times a percent. A percent times a percent is going to give me a percent squared. Does a percent squared make any sense? No. Or percent cubed? Doesn't make any sense at all. And so what I need is, I need units of percent. And so how should I do that? In other words, how can I use these numbers to tell me what the percent natural abundance of that molecule is? And this is, this is going to require some playing around, because all the percent abundances should add up to 100%. And so the way we can do this is this. We don't have to represent it as a percent. What's another way of representing a percent? A percent can be represented as a part per 100. And so what I'm going to do is, rather than using percent here, I'll just go dimensionless. And this is going to be 99.9885 out of 100. So if I have 100 of these H1s, 99.9885 would be those. Okay, I'm not going to add it, because if I add it, I'm going to go over 100%. And then what is oxygen? Oxygen is 99.757. So rather than adding it, I'm going to multiply it. 99.757 out of 100 will be oxygen 16 times. Now I need a percent. So what I'm going to do is, I'm going to use this as a percent, 99.9885%. And this is going to give me the correct units, right? And so this is figuring out the equation by dimensional analysis. I either use the fractional or the decimal form of the percent times the percent. And so let's try this. I'm going to convert it to decimal, 0.99985 times 0.99757 times 99.9885. And so according to my calculations, you just drank 99.734. How many sig figs am I allowed here? 3 because of the 100?
No, because of the, oh, never mind. I was still thinking of addition and subtraction.
Okay, no, yeah, we're doing multiplication here. Yeah, what about 5? So you just drank 99.734%. To make sure this adds up to 100, sometimes I carry an extra digit, like 0. That way I can check to make sure I didn't make a calculation error if I'm going to calculate each of these. So you drink 99.734%. So what this means is, if you drank 100,000 water molecules, 99,734 of them were H1O16, H1. What's the least abundant? H2O22? Yeah, you'd think that would be the least abundant, but you have to recall the even odd rule. Yeah. It's going to be, the least abundant is going to be this one, H2O17, H2, correct? And so what's the percent abundance of this molecule? And so let's go ahead and calculate the percent abundance. And so the percent abundance is going to equal what? So either in fractional or decimal form, we can write deuterium. I'll just write in fractional since I'm using that. It's going to be 0.0115 out of 100 will be H2. Wait a minute. Does it make a difference which one I use the percent for and which one I use the fraction for? Will that change my answer? No, it makes no difference. So you could do whatever. It's just 2 out of them have to be percent. No, one of the 3 has to be percent. The others have to be fractional or decimal. Okay, O17 is a lot less abundant. O17 is going to be 0.038 out of 100. And then we'll do the last deuterium as a percentage. And that's going to be 0.0115%. And so this is going to be times 0.00038 times 0.0115. And what do you guys get? How many sig figs am I allowed here? 2. So I'm going to go 5.0, and then I'll carry 1 extra as a subscript. 5.02 times 10 to the negative 10%. Are we out of time? Oh, shoot. Let me just let me convert this into decimal form. That's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 502%. So depending on how many water molecules you had today, you might not have had any. You'd need 1,000, million, billion. You'd need about 10 billion water molecules. If you had 10 billion water molecules, you probably had 10 billion water molecules. Then only 5 of them were this. Does that make sense? Yeah. All right, we'll stop here.